Swayam Prabha. Digital India. Educated India.
Welcome everyone to our online NPTEL course Environmental Chemistry and Microbiology. This course will be taught by Professor Sudha Goel and myself, Professor Anjali Pal. We are both from Civil Engineering Department of IIT Kharagpur. We have divided the course into two parts. First part, Environmental Chemistry, will be covered by me, and the second part, Environmental Microbiology, will be taught by Professor Sudha Goel. In the module 2, which we will start today, I will discuss about the chemical equilibrium. The chemical equilibrium, you know, is a very important topic for environmental chemistry, and in my next 5 lectures, I will throw some light on this topic. The first lecture today will cover the following topics: reversible reaction, concept on equilibrium, kinetic approach to equilibrium, laws of mass action, activity and activity coefficient. We all know that when we want to know how much product is formed or from how much reactants, we always use the balanced equation for a certain reaction. So, in molar ratio method, when we want to determine the amounts of material and the material consumed in a chemical reaction, we assume that all reactants are converted to the products. That means 100% conversion. We never consider that the products may react to form the original reactants also. But in most cases, the reaction does not go to completion. All the reactants are converted to products according to the molar coefficients given in the balanced chemical reaction. In the complete reaction, 100% conversion, but almost all the chemical reactions, they do not go to completion because the products formed react to produce the reactant. That means opposite reaction also occurs. The reactants also react, the products also react to form the reactants. That means reactants form the products, at the same time products also form the reactants. This type of reaction are called the reversible reaction. Here both the processes, that means the forward reaction and the reverse reaction, sometimes instead of reverse reaction we called the backward reaction also, they occur simultaneously. And to indicate that the reaction is reversible, we always use a double arrow in the chemical reaction. What is the equilibrium concept? The most simple equilibrium is the equilibrium of water as liquid and water as gas. That means if you take some water, that liquid water, in a closed vessel, and if you keep it for some time and you allow the reaction, the phase transfer go on at a certain temperature, then after some time the equilibrium will be reached. At that equilibrium point, the amount of water in the liquid form that is converted to gaseous form, same time the same amount of gaseous water will come back to the liquid form of water. This is not the chemical equilibrium, but it is called phase equilibrium. For chemical equilibrium, we have to consider a chemical reaction. That means, say for example, the most simple reaction has been considered here. A plus B, the molar ratio is 1:1, is converted to C and D. Here also the molar ratio is 1:1, and here you can see the double arrow is there. That means the double arrow, it is indicating that both the forward reaction, that is the reaction of A and B to form C and D, and the reverse reaction, that is the reaction of C and D to form A and B, may occur. That means forward reaction at the same time a backward reaction is occurring in this particular reaction. Now, what is equilibrium? In this case, here it is phase equilibrium, but in this case we will call it chemical equilibrium. What is chemical equilibrium? When a reaction proceeds to a point where the combination of reactants to form the products is just balanced by the reverse reaction of products combining to form the reactants, then we can say that the reaction is attained the equilibrium. That means what? At equilibrium point, what will happen? A and B will react to form C and D. At the same time, same amount of A and B will be produced by C and D. That means we can say in a simple way, no more conversion takes place. This is the chemical equilibrium. Now, there we can have this type of equilibrium by considering the kinetic approach also. The attainment of state of equilibrium depends on the speed. Say for example, we start the reaction, A and B combines and reacts to form C and D. So, when the reaction just starts, then the reaction proceeds fast, but after some time when it is reaching towards the equilibrium, then we can say that the rate of the forward reaction and the rate of the backward reaction is the same. That means, A plus B going to C plus D, that is the forward reaction, and C plus D is giving to A plus B, that is the reverse action. These two rates, so the rate of the forward reaction and the rate of the reverse reaction can be expressed mathematically, and which becomes the same. That means, the forward reaction, we know that it depends on the concentration of A and B, that is the reactant concentration, and there is a constant which is called the specific rate constant or rate constant. And then for the backward reaction, that is the rate RR, it is expressed as RR. This is rate F, means rate of the forward reaction, and this is the rate of the backward reaction. In this case, K2 into concentration of C into concentration of D, that means K2 is the rate constant for the backward reaction. So, when these two rates are same, then what happens? You can see that at equilibrium we know that the rate of the forward reaction is the same as the rate of the backward reaction or reverse reaction. Then K1 into concentration of A into concentration of B is the same as K2 into concentration of C into concentration of D. You always remember that the rate constant is always represented as small k, and equilibrium constant we always represent by capital K. In many books also I have seen that they are confused, and sometimes for the rate constant also they use the capital K, but this is not okay. Now, you can see that collecting all variable terms in one side and all constant terms in the other side, that means this is the expression, then we can tell that K1 by K2, which is another constant which can be represented by Kc or K, that is nothing but concentration of C into concentration of D by concentration of A into concentration of B. Now, this K, capital K, is called the equilibrium constant. So, this is the most simple case. I have told that all the molar stoichiometric molar ratios are 1:1:1:1, but here there is, but almost all reactions are not like that. There may be some not the molar concentration may not be 1, but it may be 2, it may be 3, it may be 4, whatever. So, considering this type of reaction where it is not 1:1, but it is 2:1, say for example, 2A plus B is giving 2C plus D, then the K will be same way, K1 by K2 is nothing but C concentration of C square into concentration of D by concentration of A square into concentration of B. But in the general reaction where A that means A is the molar concentration of A and B is the, it is the stoichiometry actually. So, if we represent in this way, then we can write that K is nothing but C to the power C into concentration of C to the power C, concentration of D to the power D by concentration of A to the power A into concentration of B to the power B, where A, B, C, D represent the stoichiometric number of particles of A, B, C and D. It is also called the law of chemical equilibrium or law of mass action, and it can be applied to many kinds of reactions as ionization reaction, precipitation reaction, dissociation type of reaction, complex ion formation. This is the basics of the chemical equilibrium. We will see many different applications of this type of expression. Now, in the equilibrium concept, some important points we have to understand when we go for the equilibrium expression. Say for example, the concentrations of A, B, C and D in equation A. What is equation A? This is the equation A, you remember it, that this is the equation A, and in this equation the A, concentration of A, concentration of B, concentration of C and concentration of D exist only at equilibrium. This is the equilibrium concentration, you must remember it, this is the equilibrium concentration. And when you get a very small value, when you obtain a very small value of K, what does it mean? That means that the equilibrium is reached after a small fraction of reactants are converted to products. That means the product obtained is less compared to the reactants that we are taking. And on the other hand, for a large value of Kc, it means that the large fraction of reactant molecules are converted to produce when the equilibrium is reached. That means which side the equilibrium is shifted, it will tell that whether it is going more towards the right hand side or it is going more towards the left hand side. That you can understand from the value of Kc. For a system in equilibrium, an increase in reactant concentration, this is law of mass action. When you increase the reactant concentration, say for example, some system is in equilibrium, now you increase the reactant concentration, then what will happen? It will go towards the right, the forward reaction will go on. On the other hand, if you increase the product concentration, then it will go to the reverse direction. This is the actually this is explained by the La Chatelier principle. Okay, I will go to this later, but for the time being you please remember this thing that K value is constant, but how much it is towards the right hand side or it is towards the left hand side, that will be decided by the concentration of the reactants and the products. Now, this is very important for the process engineers or the environmental engineers or chemistry students, analytical chemists. This is very general, this is very basic concept for chemical equilibrium. Now, let us consider another example which you can visualize, because this has different colors. You can see it is the NO2 gas. NO2 gas is brown, red brown in color, okay? And the N2O4, which is the dimer of NO2, this is also gas. This has no color, okay? Now, think about this reaction. This is the equilibrium expression. So, depending on the condition, that means the temperature, you can see different colors. If you take NO2 in a closed vessel, if you cool it or if you heat it, you will see the two different colors that is prevailing. Okay. Now, here you can see the N2O4 the red brown color, when the NO2 goes to N2O4, the red brown color is restored. Okay. So, N2O4 has no color. So, you can see here NO2 when goes to N2O4, then this color is you see it goes on upon cooling, and you will see that the NO2 has color, but when it goes to N2O4 the color is not there, and it happens upon cooling. Okay. And the reverse reaction, that means N2O4 goes to NO2 when the temperature is raised, that means the here you see that there is no color, and then it goes to NO2, and so red brown color is restored. You can see it, you can visualize it, because the two different things are two different colors, that is why you can see it when you do it in a closed vessel and if you properly maintain the temperature. Okay. At high temperatures, the intense red brown color indicates that NO2 predominates. Okay. At equilibrium, the rates of forward and reverse reactions are equal, and there is no further net change in the partial pressures of reactants or products. Okay. This is the equilibrium condition. Okay. And the experimental value of K is 8.8 at 25 degrees centigrade. You will always see that when the K value is mentioned, we must tell about the temperature, because it varies with temperature. We have also seen when I explained the acid bases, I have told that either K value or Kb value or Kw value, I have mentioned about the temperature. So, temperature is very important. Now, if we express both in terms of partial pressure, then this value is like that. Okay. If we express in some other different ways, then maybe K value will be different. Now, N2O4 are expressed in atmosphere, both NO2 and N2O4, the partial pressures are expressed in atmosphere, therefore, the NO2 N2O4 reaction mixture is in equilibrium as we see here, and then at the particular temperature, at a particular temperature, say at 25 degrees centigrade, the equilibrium expression will be like this. You have to consider this, then K is nothing but the, here it is partial pressure because it is gas. So, partial pressure of N2O4 by partial pressure of NO2 to the power 2, that means square. Okay. This is the expression. This expression you always do in case of either gaseous equilibrium or in the aqueous equilibrium. So, concept is the same, but you have to use different types of concentrations. In terms of gas, if it is gas, then you have to use the partial pressure. If it is in ion form in the aqueous solution, then moles per liter. Now, activity and activity coefficient, this is also very important for equilibrium relationship. We always use it is expected that we always use the dilute solution. When it is dilute solutions, then concentration we should express the concentration in moles per liter. But as the concentration is increased, then that means not for very dilute solution, but the concentration is higher, then this activity term should come. Why? Because when there are many ions, then they have the influence on each other. In that case, it is noted that as solutions of ionized materials become more concentrated, their quantitative effect in equilibrium relationships become progressively less than calculated solely from the change in molar concentration. That means, in that case, at higher concentration, the molar concentration if we use, then there may be some error. Okay. Hence, the effective concentration we have to use, which is also called activity. Okay. And the expression, the relationship between the activity and the concentration is like that. This is the activity coefficient. So, when we express the activity, we use the second bracket. When we use the concentration, it is in moles per liter, then this is the third bracket. Okay. And this is the activity coefficient. So, in case of dilute solution, we can tell the activity is same as the concentration. Okay. But in case of in case of not dilute solution, but concentrated solution, we have to consider the activity term. Although numerical calculations from equilibrium relationship may be erroneous in actual concentrations if actual concentrations are used in place of activities, but the error is not very great for dilute aqueous solution. In that case, we can consider that activity is same as the concentration, and we use mostly the dilute solution. So, there will be not much error. For practical purpose, the rough calculations obtained using molar concentrations are sufficient. That means, we do not have to bother that we have to use the activity term. Okay. Besides this, the activity coefficient, not only this, to determine the activity coefficient is not a very easy task. We cannot determine it with precision. This is partly because the activity coefficient is influenced by presence of other ions. That means, for practical purpose, we use the concentration term and we ignore this activity coefficient. The one reason is that it is very difficult to determine this thing. Another thing is, it is for practical purpose, it is sufficient to use the concentration. We do not have to use always the activity term. Now, the activity, if we use the activity term, say for example, we are using the activity, we want to use more accurately. So, we will use the activity term. Then in this reaction, for this reaction where A moles of A reacts with B moles of B and then produces C moles of C and D moles of D, then in that case K should follow this expression. That means, C, it is the second bracket. So, it is the activity. So, in all cases we have to use the activity terms. Okay. And then we all know that activity is nothing but activity coefficient into concentration. Okay. And then for dilute solution, we can think that activity is the same as the concentration. That means, we can straightforward we can use this expression. But we have to know this, because it is very important to know this in case of concentrated solutions. In that case we must consider the activity and activity coefficient. Now, some rules to be followed. When you think about the equilibrium expression, then you have to follow some rules. What is the rules? In case of ions and molecules in dilute solution, concentration is expressed in moles per liter. So, it is the aqueous solution. So, there we have to use the concentration of ions in terms of moles per liter. Now, solvent in a dilute solution. The concentration is taken as unity. There is some solvent in a dilute solution. So, for this we have to take the concentration as unity. Now, when some pure solids or pure liquids in equilibrium with the solution, we will get some examples later, but here just I am writing the rules here. For pure solids or liquids which is in equilibrium, in case of say heterogeneous equilibrium where all are not in the same phase, then it is called heterogeneous equilibrium. In that case, pure solids or liquids in equilibrium with the solution, then the concentration is taken as unity. When there is a mixtures of liquids, then the concentration should be expressed in mole fraction. Okay. And in case of gases, we have already seen that NO2 and N2O4, that equilibrium we have seen. In that case, say for example, we have used the partial pressure. So, in gas phase, when the reaction goes on, the concentration we have to use in terms of partial pressure in atmosphere. Okay. These are the rules that we have to follow when we develop some equilibrium expression, because otherwise everything will be wrong. Now, for this part we can use textbooks, any textbooks, physical chemistry textbooks or inorganic chemistry, some inorganic chemistry textbooks also this equilibrium concept is there. And I have given two references, but you can have this explanations in many books. You can consult these books or other books also. This is Sauer McCarthy. I have already given these two references in case of acids, bases and salts when in the module 1. I am giving the same reference here, and thank you for hearing this first lecture for this module 2, that is the lecture number 6. Thank you.